Hello, let's discuss k-means clustering. So let's Google k-means clustering. Uh, I think there are many good explanations, but let's check Wikipedia. So k-means clustering. Okay, so k-means clustering is a method of factor quantization. We can skip this. Originally from signal processing. Also skip this. That aim to partition. Okay, now we have important part. The aim of k-means clustering is to partition n observations into k number of clusters. So in which each observation belongs to the cluster with the nearest mean, cluster center or cluster centroid. So it means, so suppose this is plane and we have this data, then we basically partition the data such that, partition the data such that each observation belongs to the cluster with the nearest mean. So suppose this x is the mean. So yes, something like this. So we have this data. So each data, so V belongs to this segment because it is nearest to the X. Okay, this one. So instead of this one or this one or this one, this V is nearest to this one. So it belongs to this one, this cluster. This circle is nearest to this X instead of this or this. Okay, so that's why this circle belongs to this cluster. Okay, so each observation belongs to a cluster with the nearest mean. Because we have k clusters, so it means there should be k number of means. So those means serve as a prototype of the cluster. So basically, this results in a partitioning of the data into Voronoi cells. Okay, Voronoi cells. So k-means clustering is partition of data, partitioning data space into Voronoi cells. Voronoi cells is, I think, important, so let's check it. So Voronoi cells, I think this is a wonderful figure over here. Voronoi cells, okay? So we have a seed to the black circle. Black circles are seed, and we are partitioning this plane into several segments, the blue segment, like a green, pink segment, sky blue, and blue. And then each point, like for example, every point over here, they are nearest to this one. Okay, compared to this one, no, it is nearest to this one. So this point, uh, and then for example, we have this point. Yeah, suppose this point is nearest to this one. So this point in green, every point in green is nearest to this one. Okay, so basically this Voronoi cells means that given given this seed, black circle, we partition the entire plane like this way. These Voronoi cells. Okay, so in mathematics, a Voronoi diagram is a partition of a plane into regions close to each of a given set of objects. In the simplest case, these objects are just finitely many points in the plane. Okay, so basically, therefore, now, yeah, this K-means clustering is basically a partition of data space into Voronoi cells. So K-means clustering minimizes within cluster variance, squared Euclidean distance, but not regular Euclidean distance. So here, distance means that it is the within cluster variance. So basically, it minimizes x minus mu square. Okay, so it minimizes square. So in the previous Voronoi space, so like this one, every point here is nearest to this point in terms of this measure. Okay, so this is the way of measuring the distance. In a K-means clustering, of course, we can use Euclidean distance, but that is more complicated, computationally complex, which is Weber problem. So instead of simply Euclidean distance, we minimize variance, basically square the Euclidean distance. Yeah, and then okay, so uh, yeah, the mean optimizes squared error, whereas only the geometric median minimizes Euclidean distance. So we are looking for means, not median, because mean minimized the squared Euclidean distance. So the problem is computationally difficult. This K-means clustering, basically clustering, segmenting the data, partitioning data is computationally difficult. However, fortunately, we have efficient heuristic algorithm. Okay, converge quickly to local optimum. We will discuss this heuristic method shortly. Okay. Anyway, let's skip and the description. Okay, we have description of the K-means clustering. So given a set of observation x1, x2, xn, so we have n number of data. Okay, where each observation is d-dimensional real vector. So they are the vectors x1, x2, xn. They are vectors which have like d-dimensional real vector. Dimension is d. And then K means clustering. Okay, what is K means clustering? K means clustering aims to partition this n observation. We want to partition this n observation into K sets. Okay, K of course, because we are partitioning n into K, so K should be smaller than n. So we are partitioning this data into K sets, and we will call this set as big S, which is collection of S1, S2, Sk. So the S1, S2, Sk are each are also sets, which include partition of this one. And then the question is how we can define these each sets. Okay, how we can partition this n number of data into cases. We partition so as to minimize the within cluster sum of squares. So in each cluster, sum of square in each cluster like Sk or S1 in each cluster within cluster sum of square is minimal. So formally the objective is to find this one. So we minimize. So we have a cases. So there are, yes, so here, very interesting. So let's look at this part. So when we have x is in SI, suppose in x is SI, then this x minus mu I is basically center of this SI, center of SI. So basically this is the squared distance of x from the center of the SI. Okay, so again, this is square. This is the measure of distance, squared Euclidean distance, and then we sum all the distance, and we want to minimize this all the sum of differences by selecting appropriate s. Of course, since this is variance, and then so variance divided by, of course, the size of the SI, number of SI. So we can write down this one into this formula. So they are basically same. Of course, we can uh, this x mu I into the y, so that because it's a mean, so basically we can redefine this one as the like within minimizing the pairwise squared deviation point in the same cluster. Pairwise, of course, we have to because it's pairwise, we divide by 2, and then yeah, number of, because we are the average out, so number. Okay, the equivalence, they are equivalent because of this relationship over here. This is equal to maximizing the sum of the squared deviation between points in different clusters, which follows from the law of total variance. Okay, now history, you can skip to history. So, well, we have mathematics over here. Then the question is how to implement this mathematics. There is a very interesting algorithm. So standard algorithm, naive k-means. Okay, so let's go through this. The most common algorithm uses an iterative refinement technique. So iterative refinement technique. Due to ubiquity, it is often called the K-means algorithm. K-means algorithm. It is also referred to as a Lewis algorithm, particularly in the computer science community. Okay, so same K-means algorithm is Lewis algorithm. You know, it is sometimes also referred as a naive K-means. So we have naive K-means, Lewis algorithm, the K-means algorithm, they are all same. Okay, it is naive, of course, it's naive because they are exist much faster alternatives. But this naive K-means algorithm is most intuitive, so I'm gonna explain that. So then, what is the standard naive K-means algorithm? Okay, now because we need to partition data into K segment, K sets. So we just select the initial set of K-means. Just pick, basically we are picking arbitrary K numbers. Usually we pick these K numbers out of data. Okay, select K arbitrary data and we can call them as the first seed of the K-means. And then the algorithm proceeds by the alternating between the next two steps. So now we have arbitrary first k number of means. Now next, what we do is assign each observation to the cluster with the nearest mean. Okay, so now we have this initial means. So suppose we have data. Suppose we have some data like x1. Okay, and then we measure the distance between this one, basically this one, and this one. Okay, so when x1 is nearest to this one, then x1 belongs to s1. Okay, so assign each observation to the cluster with the nearest mean. That with the least squared again, the distance is this one, square, not Euclidean distance, it is square. Least squared Euclidean distance. So mathematically, this means partitioning the observation according to Boroi diagram generated by the means we saw before. So again, well, given this initial one, then xp, okay, some xp belongs to Si when xp distance between xp and mi is smallest compared to others over here, then it belongs to Si. Okay, and we to everything. So if we have n number of data, we iterate from x1, x2, and xn, and everything. Measure the distance between this one and assign that to each one. Okay, it's a one. And then next, once we do that, so now we basically what we did is we assign each observation into k number of sets, right? Then the next step is recalculated mean. Okay, now we update this m. We updated this m over here. How? Well, we have new sets, k number of new sets, and each set will recalculate mean. Okay, average. So our next stage mean is, so for every xj which belongs to Si, we average it. So we recalculate the center. Okay, so we have a new center. Okay, so we have a new center of m1 to mk. Now we do the same thing over here. Now we have x1 to xn data, x1, x2, and xn. So again, we measure the distance each one and find the nearest one and assign this one into the set corresponding to nearest distance to one of these m. Once we have clusters, then we again calculate the centroid of each cluster, and then we repeat and repeat several times. Okay, until when we repeat this process, until assignment doesn't change. Okay, so the algorithm has converged. We stop when assignments no longer change. The algorithm is not guaranteed to find the optimum. Maybe it is the algorithm not guaranteed to find the optimum. We may stuck into some local optimum, but in many cases it find. Okay. The algorithm is often presented as assigning object to the nearest cluster by distance using a different distance function over other than squared Euclidean distance. We use Euclidean distance may prevent algorithm from converging. Okay, which means that squared Euclidean distance always converge. Various modifications of k-means such as spherical k-means and k-medoids, it's like a median measure, have been proposed to allow using other distance measures. I think it is enough, but well, let me explain again. So again, what we do is suppose like we have 2D plane. Suppose we have 2D plane, and then suppose we have like this number of data, bunch of data. Okay, we have this data, and suppose uh, we want to cluster this data into like a two sets, two, so k equal to here. So step one, okay, in the step one is we just select randomly select like a two data point, like pick this one and this one at the first step, pick this one and this one, then, well, pick this one and this one, let's say this is square. So this one is close to, so this one is a circle, this one is a square. Now, for each data, we measure the distance. So this is measure distance between this and this one. Obviously, this one is close to circle. Okay, so it is becomes a circle. How about this one? This one is, well, close to circle, so it is a circle. It is a circle. Well, it is a circle. This is a circle. This is close to circle. Now this is this and this. I think it is close to circle. So it is circle. And this one measure the distance. Then this is close to square. And this is the measure the distance. So it is close to square. So it becomes a square. Okay. And the square. So in the square, square, and the square, right? And then, well, of course, this is square, circle. Now we have this cluster, okay? This cluster, now we have this cluster, right? And in each cluster, we again calculate. Now, this is not a center anymore. So new center would be around here. And here, new center would be around here, okay? Now, we calculate distance again. Now, well, this one, okay? It is new center. Now, this one, we measure distance between these two. So it is close to circle. Now it becomes a circle. Okay. It is circle. Okay. So we delete this one. So change this one into circle. Okay. Change it into circle. Okay. And then this one is fine. This one. So I think nothing changes. Now new area looks like this one. This is now circle area. This is now square area. Now we calculate the center again. Now center is somewhere over here. Now center is somewhere over here. Now even now next, this one is now close to circle, possibly let's assume that. Now this one becomes maybe this one becomes the circle. Okay. Then we have this area. Then center is somewhere here. And then here, this is square. Then we center is somewhere here. Now nothing more changes. So we iterate this process, and this is called K-means clustering.